Let's talk about how we report the results in APA style. So I'm assuming you just watched the video on how to calculate to perform the Z test on this college group to see if that it's grown. Um, in the example, I wrote up one summary. Here's another summary, somewhat different, that explains some of the details that you need to have in to report the results. So what I wrote was that the long-term average attendance in a college group, and then I put M for mean equals 100 and standard deviation equals 10. Those are the standard APA abbreviations for the mean and standard deviation when you're talking about some variable. Notice that they don't need to have any subscripts on it, and they don't need to have any fancy character like X bar that is hard to prepare. So the long-term average attendance in a college group was compared to the average of a sample after an outreach activity, and then I give the information for the sample, n equals 4, mean equals 105. So I gave the information for the population, mean equals 100, standard deviation equals 10, and I said that was compared to the average of a sample. That's what a Z-test does. Although the sample attendance was larger than the long-term attendance, and I know that this difference was 5, so we got some evidence that the group has grown, this difference wasn't significant. And specifically, we're using significant in the statistics term. And to report significance, we need to report the statistics. I put Z equals 1.00. Notice how Z is in italics. And then I gave the probability of obtaining that results by chance, P equals 0.32. And I clarified that this is a two-tailed test. Now, because P is greater than 0.05, we all know that that means that it's not significant. It's assumed that having a high P values means that it's not significant. So that's why we put all this in the parentheses there to let people know exactly how much we can trust this result of the difference of 5. And because the P value is so high, we can't really trust it because it could have happened by chance real easily. Now, a different way of testing to see if something's significant is instead of calculating the exact p-value like Excel does or other statistics programs, we could use what's known as the critical value of the Z, kind of like a cutoff statistic. So this is kind of like a shortcut so that you can just look at the Z statistic and you don't have to look up probability. It's becoming less and less relevant now that we have computers doing all of the calculations, but conceptually it's a good idea to understand. So let's go back to our idea that we were going to have our alpha is 0.05, and we're going to look at a two-tailed test. We want to see if the results have less than a 5% chance of occurring if the null hypothesis is true, and we're looking at both ends of the tails, both extremes, in case when we're interested in both really high scores and really low scores. So with alpha equals 0.05, we look up a value of Z such that 5% of the scores will be in these two tails. That'll be the rejection region. So it'll be 2.5% of the scores will be here, and 2.5% of the scores will be there. And it turns out the value for Z for this is 1.96 and minus 1.96. So we say that the critical value of Z, or Z crit, is 1.96 for a two-tailed test when alpha equals 0.05. So what this means is we just need to calculate the Z obtained. Our Z is our test statistic. Take the absolute value of it. That means drop off any negative signs that are there. And if that's greater than our critical value, we reject the null hypothesis. In our example, the absolute value of 1, our Z statistic, was less than 1, so we retained the null hypothesis. The group might not have grown. So if we have a large Z statistic, or large any statistic, that means a low p-value, and we reject the null hypothesis. So try to keep that in mind, that if you're trying to reject the null hypothesis, a large statistic is good, and a low probability is good. Those two go hand in hand. So that's the critical value for Z of 1.96 for two-tailed tests. And so whenever you know that you're doing a two-tailed test and your z is greater than 1.96 or greater than 2 for practical purposes, you know that it's probably not happening by chance. We can reject the null hypothesis. In a one-tailed test, where we're going to say, oh, it's going to be below this number, or it's going to be greater than the mean, we can have all 5% on one side, and that changes the z critical value to 1.645. If our hypothesis is predicting something that increases, the z-crit would be 1.645. If our hypothesis is predicting that it decreases, the z-crit would be minus 1.645. And this would be for a one-tailed test. So you can see that if we have a directional test, a one-tailed test, we don't need to get such a high z. Before we had to get a z of 1.96. If we make a one-tailed test, we only need to get a z of 1.645, so it's easier to reject the null hypothesis. Let's go back to our college group example, and suppose that the group averages 105 for 4 months, for 16 weeks. Now, can we say that's change size? So we're going to look at the same group, same example, same first 4 weeks, but now we have more data. The average is staying at 105, but by the fact of having more data, will this enable us to reject the null hypothesis? And we'll look at the calculations in detail on Excel.